Hello, and welcome to another episode of Undercooled. Today we have an awesome guest, Tricia Nguyen. I used to know her as Tricia Wilson, and she was a graduate student in our department with Dave Martin several years ago, and now she's on our external advisory board. And boy, does she do some interesting stuff. So we're really happy to have Tricia on talking about uh, materials, but the kind of materials that most people think about: fabrics and threads and embroidery. So go ahead, Tim, ask the first question.
Sure thing. Tricia, welcome to the show. Very happy to have you here. We usually just
Hi.
start with introductions. The audience is very sick of me and Steve at this point, but you are a fresh face. So just
I
tell
am a
us,
fresh face.
who you are. Where do you come from? How did you end up on this lovely show with us?
Oh my gosh. I don't know how I've ended up on this lovely show with you guys, actually. But well, I'm from Michigan originally, and I grew up in the middle of the state, and kind of like a lot of kids, got interested in a lot of different things, and I somehow ended up in this incredibly strange career that I've developed for myself as I know you guys have just kind of mentioned fabrics. I was at University of Michigan, did my PhD there in dislocation theory of polymers, in fact. And I went from dislocation theory in polymers to 17th century Renaissance embroidery. And it seems like that's a really big of a disconnect, but it isn't. Um, Along the way, I've been a product engineer. I have been an entrepreneur. I've formed 3 companies, and I've been a STEM teacher, and I've been a professional embroiderer. So it's really hard. My kids have a really difficult time when somebody asks them, because they're in college now, and then somebody asks them, "What do your parents do?" And my son goes, "Oh," in that roll the eye kind of a
Oh
thing,
yeah.
and said, "Do you have 30 minutes?" And he says, "It requires visuals, Mom, to tell people what you do." And I'm kind of proud that he actually doesn't just discount it and say, "Oh, she teaches embroidery."
Right.
But it's yeah, I don't know where you want me to expand. It's there's so much to expand on, Tim.
Well, let's start at the very beginning. How did you
Well,
get into material science in the first place? What was your entry route?
you know, my entry route is the same as the chair of your department. There was a series of STEM education summer camps in engineering at Purdue and Michigan Tech University. Great entry points. They were for girls. And I was just nominated by my high school to go attend them. And while I was there, I got to experience material science, as you know, along with all of the other really cool things. Like I did get to let the dynamite go inside the mine up in Michigan Tech. That was pretty interesting and kind of interesting, intriguing. Maybe blow things up. Um, but I was also interested in space at the time. We would send out Voyager, and I was very interested in the space shuttle. And I thought, oh, maybe I'll be an astronaut, like some kids, fireman, astronaut. Maybe I'll be an astronaut.
Oh, I definitely
And
had the astronaut phase
did you have the astronaut phase too?
for sure.
Oh, that was a long phase in my life, into graduate school and postgraduate school, in fact. But if you were a woman, the only route in at my time was as a material scientist, really, as somebody who would be a mission specialist. And I even went the route of trying to go to the Air Force and become a pilot. And somebody whispered to me on the side and said, "They're not going to let you fly," because I was a woman at the time. And things have changed since then. But so I thought, well, I'll go into material science because I want to be an astronaut. And here I am studying Renaissance embroidery. Kind of, kind of interesting. So that was my route in.
Wow, that's pretty cool. So you said you started several companies. Can you tell us
Yes.
what you started, what you did?
Well, so I left research engineering about 20 years ago, and as Tim knows, I told this to the students when I came to the University of Michigan recently. I gave a talk on my career, and I thought it was really important to tell the students, not to kind of bang the chest and say, wow, I've done a really great job and I have a really interesting career, but also to tell them that, hey, you just don't know what path you're on. And I really feel like what I'm really good at is failure, is just failing and figuring out what to do from that failure. So I ended up with an arm injury at the end of a very intense project that I was leading at a research corporation to redesign the soldier system for the US Army. And so I was working quite a bit, and I injured my right hand so badly that I couldn't feel it anymore. And I knew that because I was writing proposals, grant proposals for material science research and doing things like that, that I was not going to be able to type for a long time. And of course, I also wasn't going to be able to embroider either. So I figured that I needed to do something else, and I needed to do something where I could control my time. So I started a consulting company in electronic textiles, which was a field that I had started and which is the reason I was working on this Army project. And that allowed me to really use my voice more than anything else than typing. So did consulting engineering in that for about 15 years. Concurrently, because I was still very interested in embroidery, I said, well, what if I never get my hand function back? I really need to have something where I'm not selling hours typing. I need to have something where I am selling pieces. And so I started a product company based on a paper product that was made in the Victorian era, which they used punches. Think about a stamp, and you have the holes around the edges of the stamps perforated. But if you put those in an array, that is analogous to a piece of graph paper or analogous to a piece of linen. And you're able to stitch between the holes on the linen. So you'd be able to stitch between the holes on the paper. There is a really gross scale version of that that's popular in the craft market today, and I wanted to make it more petite, more delicate looking, and prettier. So in the 1800s, right around the times that stamp perforation was developed, Valentines. Maybe some of people know about lacy Valentines. Well, the same companies that made these lacy Valentines used the perforation technology to perforate the center of them, and women would embroider on it. Beautiful. So I brought that technology back. It's was very expensive to do dyes to do that kind of cutting, and I said, hey, lasers. I had done a lot of work in laser holography in my early career. And I said, oh, I know about steering lasers. And maybe we could actually use that to cut the holes in very high quality paper. And so we did. So I had a company that did that for, 15 years ish. Um, Unfortunately, and I would talk about failure here, uh, the collapse of the 2008 stock market crash tanked that company because our we had to use subcontractors to do all of the manufacturing, and they were all stationary companies. They were, in fact, the original companies that made these lacy Valentines that were
Oh,
in the
wow.
Massachusetts. Yeah, it was the center of Massachusetts. That was where that whole industry had been in the Victorian era. And so I was using the kind of antecedents of that. And they mostly greeting card industry, they're funded, they get a loan at the end of the year that takes them for their cash flow for the whole year. Well, the 2008 crash was at the end of the year. Banks would not loan, and all the stationery companies, most of them, went out of business in Massachusetts in 2 months. And so all my subcontractors were gone. And so it was very difficult to keep going because they sold all of the equipment on auction. So sometimes you learn a lot from that type of thing. So that one went away. And then I have a third company, and this is where I think we'll show you one of the visuals for those who are watching on YouTube, which is Thistle Threads. And that company I started in 2000. And that was um, what happened there was I was still working for many years in engineering and pure high tech, self assembled molecules, all kind of really great stuff. But I was going to have kids, and I knew that my kids were likely going to be dyslexic like I am. And I thought, I might need a backup plan if I need to spend some more time, part time, etc. And so I started this company called Thistle Threads, which was the historic embroidery portion of my life. I had been a historic embroiderer since I was really young. My mother started teaching me at 4 years old how to embroider. By the time I was 12, I was just eating up techniques, historic techniques from around the world like crazy. I was entering competitions, I was teaching, and I had kind of a point at which the question was, do I go to engineering school or do I go actually to Japan and become a professional embroiderer? And I decided to go to school, to engineering school, which was probably a really good choice. I might be otherwise sitting somewhere just, stitching away. Um, but along the way, I was teaching so much, and my material science just started to intersect that historic business that I started this company that allowed me to manufacture threads and sell them into the craft industry, in the really high end of the craft industry.
If we can actually
That's
go back to that decision point for a second, because this is
Yeah.
so interesting. And one thing that I notice about material science students is they tend to have very broad interests. We have students who
Yes.
dual major in music and in foreign languages and all of these things. And sometimes students will come and say, I don't know which way to go with this. I've got my engineering degree, but I'm really passionate about my creative pursuits. Like, how
Yes.
do I try to bring them together? Do I just make one of them my career and one of them my hobby? So, what's some
I think
advice
the
that you
answer
might
is
offer on
yes,
that?
yes, yes. Yes, 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 because you never know how they might come together in the end. I mean, I think that all great discoveries are usually made at the intersection of two fields. It's also an area where there is no ceiling, in a way. At one point, we realized in the electronic textiles industry that all of the people at the top were women, and we there was a film made about us, and we're like, why is that? And my point was, there's nothing above us. Nobody, maybe if we wanted to work just in material science or just in electronics, we had, there was a lot of ceiling above us. But if we combined the two, there was no ceiling, so we could just rock it up. So it happens that way in discoveries. It happens that way in career path when you kind of take two things and mix them together, and you don't necessarily know right away where that mixing is going to happen. It might be at the end of your career, it might be in the middle of your career. You have no idea. But you see a lot today with, let's say, robotics and filmmaking. And for me, it's embroidery and material science. It's there's so many ways to combine things. I think people should always like get a minor in something else because it might lead to a second career when they're done with their first career. Because a lot of people move around about every 7 years in their career. Make some money, get some stability first, and then see whether or not those other creativities can come along. I actually minored in materials science, archaeology, and anthropology when I was at MIT, and that's kind of what led me here. Um, so that's the advice I would give.
it. So I've recently taught a course with an archaeologist.
Ooh,
We taught a course called Making Things, 3 million years of materials and culture. And,
yes.
so I gave a talk about, whatever age we were talking about, talked about the material science of it. And the next day, Rob Beck would talk about the archaeology of it. And
Mm-hmm.
then we had a team-based class on Fridays. We had students from all over the entire university, so many disciplines. So we mixed all the disciplines. They worked on projects related to it. But
That's awesome.
recently, we have had a guest on, Ron Kander, who was the dean. He just retired. He was the dean of the engineering school at Philadelphia University,
Oh yeah.
and they merged with Thomas Jefferson
Mm-hmm.
University. He was the founding dean of the engineering school because the original school, you probably know this,
I do
was
know
the
this.
Philadelphia College of
College of Textiles.
Textiles, which
Yes,
is
I know many
very
people
old.
there. Yes.
And so that program has very unique degrees. You know, they have like 20,
Right.
30 degrees, combining everything from hardcore science of fibers
Yes.
to art, right?
Yes.
And so,
Yes.
so you are aware of that. So you
I'm
might
very aware of
enjoy.
that. I know many. I know many of the people of these universities, and the funny thing is, I don't know if you know, but a lot of material science departments grew out of textile departments.
Yeah,
MIT's did. So
I didn't know that. I know
yeah,
Virginia Tech is very involved in fibers.
yeah,
But
and
anyway, you might enjoy
Drexel,
watching
yeah,
our
yeah, I
discussion with
will,
Ron Cantor. He's a great guy.
I
But
will.
when students, I was the undergraduate advisor for several years, and when students came to me and said they were interested in fibers, you know, I would direct them there as a good place to go to get a master's
Yes.
to really further their career using all these credentials. And I put them in contact. No one took my advice, but you know, but we
They
have
never
had
do.
students. We have had students who've just gone into industry, like to Nike and other
Yes.
places where they are doing that kind of work. So,
Well, there's so much work in textiles going on, high-tech textiles, and now
oh
functional
yeah,
textiles, of
right,
course, which what's what we started with electronic textiles and moved into functional textiles, and it's ubiquitous, really.
yeah.
So it's not really a surprise.
I remember when you did talks at the MRS meeting in Boston about your electronic
Oh, that's
um,
right.
stuff, because
Yeah.
you had made there was even a fashion show one year.
Yes. Yes.
Were you involved in that fashion show?
I never made anything for the fashion show because I was, of course, my fashion show was military equipment. It
Yeah.
was antenna systems that wrapped around the body, or full on Ethernet going through fabric, which I actually have, I think, a picture of here for those on the YouTube. Um, and this actually is a little story, if I could deviate here, that's
Sure.
interesting. How you just never know the work that you do in some project and how it might apply. So when I was doing my graduate work, I was working for Dave Martin, and we were looking at polymer crystals that would polymerize across defect boundaries. And so we were making specific defects and watching, doing electron microscopy, looking at diffraction patterns, and looking at twist and tilt boundaries. So I had to do all kinds of things called O-lattice theory to look at, well, where is the crossover happening in order for the polymerization to occur in any sort of dislocation in one of these kind of twist boundaries. And we got to the point in electronic textiles where we were dealing with, maybe you have battery in the back and you have data in the front of the garment. You have to get across a seam boundary. It's wonderful to make a electrical circuit in a big piece of cloth, but if you don't cut it up and put it back together again, it's never going to be made into something useful. So what happens when you cut the electrical lines and you have to seam it back together? And as we were working on these military seams, all of a sudden it hit me one day, this is a twist boundary inside this seam where the two pieces of fabric are overlapping inside of what this particular military seam, which is used for all of the battle dress uniforms. And I said, I know how to solve that problem of where do the electrical lines that we've woven into this fabric touch? Oh, lattice theory. So we have a patent on it. And we
That's
did,
cool.
it was moire fringes and all that. And the idea is if you could predict it at the seam boundary, you could either design the fabric, the electrical lines going through the fabric at spacings that would automatically give you the ability to do ultrasonic welding to melt the coating, which was insulating the electrical thread that you had woven into the fabric. Or you could, figure out from post how to do that and make the head. So you could go to a really fast industrial scale up of it. So
That's cool.
that was right directly from my PhD. I was like,
Yeah.
I was like, you know how you shut your PhD sometimes and your thesis, and you're like, well, I'll never use that again. Well,
Oh yeah.
Well,
I
I look at
have,
those images. They look like twins.
they do,
But
don't they?
you're looking about the details at the interface.
It's the
You know, they
interface
model, so in
inside.
metals,
Yeah.
they model a low angle tilt boundary as a
Yes,
bunch of edge dislocations.
exactly.
But of course, in
But
polymers, it's more complicated,
it's
right?
more complicated in polymers. But in this particular case, normally you take a piece of fabric and you put it together, the face to the face, and you sew a seam and then you fold it open. In a
Uh-huh.
military seam, you actually do what if you were to put your hands together and
Hmm.
fold your fingers back. So you're kind of like, and then you're trying to pull apart. There's an inside where your fingers are touching, and that is actually a twist boundary instead of
Okay.
a tilt boundary. So while it looks like a tilt boundary, it's actually a twist boundary where the interface is
Ah,
inside of the
Hmm.
seam.
very
So
cool.
who knew? I ended up with another strange situation here. I'm going to go to this another random story because I know people are going to be like, well, why is this embroiderer on on here? So for those who are listening to this, at some point, go to the internet and look up something called the Plymouth jacket. The Plymouth jacket is a 1620s embroidered waistcoat. So it's a form-fitting jacket, and it's all embroidered in silk and gold, and with gold lace all around it. And this was worn by upper middle class people and the fabulously wealthy in England during the Stuart era. Plymouth Plantation, which is a living history museum, actually asked me to run an enormous professional workshop to make one of these, and it's called Experimental Archaeology. It was for an exhibition of their that they wanted to put on. It was a multi-year project, and I had 350 people work on it. Well, great, and it became very famous object, and there was an exhibition that I was invited to speak at the Metropolitan Museum of Art, and I'm standing there next to their jacket. There's only 15 of these left in the world, but there's about like 300 portraits of women wearing them, and they're standing. I'm standing next to it, and I make a mention of how long it took, and that these jackets were originally made in professional workshops, so there'd be multiple people working on them. And somebody standing there, happened to be a guy who was a curator, said, "Nope, you're wrong." And I'm like looking at him going, "Oh my God, I just led 350 people to make one of these. Nope, you're wrong. You're wrong. This was made by a woman as she was waiting for her lover to come back from overseas, pining away in the corner." And this is a trope that is used in embroidery constantly to devalue the workmanship and that goes into these things. And I was so mad, and it became obvious to me that this was a he said she said situation. And anytime you make me mad, people who know me very well, I bring out the math.
Oh yeah.
So the engineering and the math comes out in a big way. So I thought about it, and actually I called up Dave Martin and I said, "Dave, what's being currently being used to do fast Fourier transforms? Basically, could I take diffraction patterns of the stitching on this, because it was a periodic stitching. It made a
Sure.
net, every person stitching. And I could tell as an expert that I could look at an object and say, I know that there's multiple people here, but nobody else could, because I was one of the few people in the world who was expert enough at this to know by sight. And I said, oh,
Right.
we need a analytical way to tell. So what I'm showing on the screen here is a picture of a bunch of different people's work, and it's pretty clear when you look at it, but could we divorce it down to math? And so I was able to develop a model where we took essentially diffraction patterns of this embroidery. And because I had this jacket that we had just done, and I scanned the entire thing, and don't ask me why I optically scanned it before we put it together. It's just stupid, I don't know, take data, take data, take data. And so I had this essentially control system that I was able to use, because I also knew who stitched what where on the entire thing, and prove that there were 7 people that worked on the historic piece from that. So
Did you
that was
use
just like a
Image
really
J
another
for
one of those.
this? Did you use
Yes, of
Image
course.
J? Yep.
I absolutely use Image J on this, and I still
That's a
use Image
great
J to
way.
this day.
And so you got a fingerprint of every little piece and showed that
Exactly.
the people who did, who you could identify all the different people.
All the different people. So it was like all of their little areas of embroidery, these periodic net embroidery, which we call needle lace,
Uh-huh.
were microcrystals on a
Yeah,
TEM slide. That's pretty
right.
much how I thought about it. And it really gave me a lot of insights to what a professional's embroidery looks like versus a learner's embroidery looks like, because they have all these boundary conditions of the shape of what they're teaching, what they're stitching inside. And so I speak about it in material science terms.
Right.
But this has been something that people in the historic field are very interested in.
Sure.
I love this.
Fantastic.
I'll be
So did
teaching
you,
Fourier transforms next week, so I'm
Oh,
absolutely
really?
going to use this example. It's such a good one.
Yeah, well, I'll give you a couple slides. So I'm always looking for examples of pieces of embroidery. I'm studying professional workshops right now, because I said this trope that some young lady is pining away for somebody and quietly sitting in the corner, totally obliterates the reality, which is that these were all these objects that are heavily embroidered and encrusted. Think Queen Elizabeth the First. Think King James and his court. That there is hundreds and hundreds, thousands of embroiderers slaving away to put all of this gold and silk into objects for them to wear, and it's not made by one person. So trying to bring their history back out. What I'm doing.
so I hoped you jammed this down the guy's throat who said
You
all
know,
that.
I never try to jam something down somebody's throat, but he was invited to the talk that I gave at the Metropolitan Museum of Art, which is quite an honor, about it, and he was very gracious at the end of the talk. so,
Good.
so
Well,
a lot of times it's I get mad, I use math, but then I make a friend from it.
I got to tell you this story. A friend of mine in England um, had a PhD advisor who used to come in Saturday night at like 11 o'clock at night and go rooting through all of his students' desks to see what they were
Oh
doing while they weren't
my
there.
God.
And they weren't happy about this. So my friend laid a
No.
trap for him. He took a piece of cloth, of like Oxford cloth, and with a macro lens, took a photograph of it. And he Xeroxed it a few times so it looked like an electron microscopy image.
Oh my God.
And of course, there are defects in anything, right?
Yeah,
And
yeah.
so he found a defect in a cloth and he circled it and he wrote next to it Exciton, because they were really hot then. And when they came in on Monday, his advisor said, David, I saw your work. That's wonderful. I booked you time on the National Electron Microscopy thing. Here's your tickets for the train, and here's your reservation for the hotel.
Oh my gosh. Hope we got a
So
little bit of a
how
vacation
to
out
use
of it.
fabric to to fool your
To fool
advisor.
your advisor. Well, it was actually funny when you'll remember this, Steve, but I was Dave Martin's first graduate student.
Right?
And I know probably every professor, it's tough to get your first students all set up and going, right? Recruit them. And so Dave actually came out to MIT to meet me, and said he'd seen my application. He was interested in me being his first student. And I asked him why. And the answer was because I was an embroiderer.
How about that?
And that floored me. And I said, why? And he said, because you're creative.
Yeah.
And I was like, wow, that really, I mean, now as somebody, with many years under my belt, I would do that too, because I understand the importance in creativity in research, which You know, a lot of people kind of think of engineering as being very rigorous, very mathematical, but it isn't. It's all about creativity.
Absolutely.
Yeah, that's something
Yeah.
that can be so hard to sell to students is that they're not going to be hired because of their 4.0 GPA. They're going to be hired because they're interesting, because there's
Yeah.
something about
Yes.
them that
Yes.
makes them qualitatively different from other people, not quantitatively superior or some nonsense like that.
Exactly. Well,
Yeah.
we have a flying car company in the Boston area, and my son was asked to intern there as a high school student, and he said, "Well, maybe I should drop that off my resume." And I'm like, "Absolutely not, because everybody will want to talk to the kid who worked at a flying car company."
Yeah, that's the ultimate win conversation starter. I built flying cars for a summer.
Exactly. Well, they didn't necessarily fly that well, but that's the way it is. But
Well, since
That's
we've
great.
completely thrown the script to the wind, you made me think of
I
something
know.
interesting. No, no, this is
I'm
great.
sure. Yeah.
Um, so we started talking about functional fabrics a little bit, but there's also
Yep.
astronaut phase. So have you ever thought about working on spacesuits?
I have worked on spacesuits. I've worked on so much stuff you wouldn't believe, and that's something in terms of students. If you're ever asked to go to a company that does like contract engineering or consulting engineering, especially as a first thing out of the barrel, go for it because you're going to get so much experience and so much interesting experience. So I did work with a group at MIT on spacesuits, and a company for previous to that, looking at using nitinol in the fabric to constrict the fabric as a pressure suit.
Wow.
So yeah,
Interesting.
yeah. So the number of when you're working I was working at a contract engineering firm for my first 15 years of my career, and so you would be juggling every 6 months you were juggling about 6 to 7 projects, and they could be there was a technology component of it, and then there was the application portion of it each project. So about 6 to 7 different projects, each one having 2 different areas that you had to learn. So you got very good at learning very quickly. So I might be working on a food project, such as, and I know I told this story, Tim, about trying to make a new candy that was
Right.
based on bubble wrap that you could pop, but you could eat, and trying to figure out those kind of really important questions of how does bubble wrap work, which was a lot of fun. There was a lot of putting bubble wrap down the hallway and kind of slip sliding to try to figure it out. Um, but and then maybe working on composite wings and coatings for, I know that there's some great people at University of Michigan working on this too, working on coatings that will go on wings to make the snow and ice shear off
Right.
of it as you're accelerating. So
Right.
it was crazy time. So yes, spacesuits I did work on once.
So I'm going to jump to the next thing, back to our script, because it's had a big influence on me. And that's your work with K through 12. I will never
Yes.
forget watching you do an outreach thing. I don't remember the circumstances, but you were explaining to
Oh my
little
God.
kids, you were drawing like little goldfish on the screen and saying, these are MERS. And when you put
Oh
them
my
all
God.
together,
Oh, and then
you get a
they bite each
polymer. Yeah,
chairs and they bite the
yeah,
tails. Oh my
right. I
God.
remember watching you do that, and I had never thought of it that way. And do you know, from then on my intro to materials course, that's how I always explain polymers when we first get
Really?
started. Yeah.
Oh my God, that's so cool. Well, I had a mom who is incredibly creative at teaching. She I was one of these kids who were kind of uneducatable. I'm severely dyslexic, and so I didn't go to regular school for a while. And so my mother had to find ways to teach me things before there was an awful lot of information about how to teach kids who are having difficulty reading. And she would use puppets and M&Ms and just all kinds of things. So my early formative years, Steve, were about you try anything and everything to communicate to the child in order to
Right.
do that. So you might be leading up a little bit up to, and what you're saying is that the tour guides in University of Michigan knew that I had a drawer in my lab when they would come by the lab on the tour, they could see through the window, and if I was there, they always knocked for a spontaneous, materials show to explain to kids that were visiting the college how to, what material science was. And so I always did a little dog and pony show for that, from the lab. But that has come back up again later in life. When my kids were born, I had two kids who were boys who were severely dyslexic as well. And I knew that sometimes kids like that don't get the best shake in the education system. And so I was looking constantly for something, either in a private school situation or whatever, that would give them what they needed. And what they needed, other than, big time tutoring in learning to read in a very phonics based way, was an outlet for creativity, an outlet for building, an outlet for problem solving, and something that would force them to work on something for a long period of time. And that is something that is really missing in education, is this kind of capstone project in the lower grades, because you're so often allowed to just screw up a piece of homework and then you move on. And I really felt that our kids needed something else. And my husband and I are both engineers, and we kind of took charge of our education. So, long story short, I started First Teams, and I couldn't find anybody to kind of host it. So I hosted it in my home. And for those who don't know what a First Team is, that is the robotics organization out of Manchester, New Hampshire, that's worldwide, where kids either start with like a Lego robot or they go up to metal robots. And I started kids as young as 6. So I had 2 teams, one for each child. And these kids were with me from 6 years old to 18 years old. And I had them in the house, sometimes weeknights, all weekend long, doing robotics. And so I've had this real lucky time to actually take the same kids and watch them develop the entire cycle through to becoming engineers, because they're all in engineering college now. The funny thing was that none of them were interested in engineering when they started at 6 years old. They were just kids, right? And so I know, Tim, you asked me if I would talk about a couple stories.
Sure. Yeah.
So I don't know which ones you want me to talk about. I know you and I had a side conversation about girls. Are you up for that one?
Yeah, definitely. I think I've learned so much just from talking with you about that, about like some of the cultural and societal factors that get girls off of the STEM on ramp that actually have nothing to do with their in class curricular experiences. The whole rest of the
Exactly.
world of what they live outside of class is also so influential. So,
It
can you
is
unpack
very
some of that for
influential.
us?
I will unpack some of that. So we had boys, right? And we were always looking for young girls to join our group of happy little Lego engineers. And we found many. We had, I'm trying to remember exactly, 6 girls, I think, who stayed with us for a long period of time. And in the beginning, all the little kids they're like the same, right? 8 years old, they're all the same. They're all curious, they're super creative, they're okay with failing. That's a huge one. They're okay with failing early elementary school, and which is super important in engineering. You have to let it just roll off your back, because you have to try something, it doesn't work, learn something from it, go forward, right? And as we kept getting closer to middle school, all of a sudden we started seeing the divergence of the boys and the girls, not from ability, but from the social pressures that they were under. And it wasn't because it was, oh, this is uncool. It was what's the confidence gap. And it was the beginning of that, and I'm sure you guys have all heard this confidence gap thing. And so what we saw was that as you get towards middle school, that's when a lot of social development starts. And boys are allowed out of the social development. It's okay for a boy to say, I don't want to go to that dance. And they're let off the hook. Their parents let them off the hook. They're like, I want to go do the robotics. So we'd be doing it after school. It would go to about 9 o'clock at night on a Friday night. And somewhere around 6 o'clock, parent would show up and they would take the girl away because the girl had to go to the sleepover, the school dance, whatever like that. The thing which was in middle school promoting social activity. And the girl wasn't allowed to say no because they would be, it just culturally was not allowed, you know. Now they're going to be ostracized by the rest of the girls in the class, etc. So they had to make an appearance and show up. So here they are. They're they're all working together on this robot, their attachments, their programming, whatever it is. And the girls leave to go to the sleepover. The boys continue on. The girls come back the next day to make up time, but they automatically were like, oh, I don't want to change that with my maybe better idea because he worked so much on that. And this beginning of the confidence gap, is that they just had these periods of time where they were taken away from it. And my husband and I we were like, what's happening? Because now they're starting to recede into themselves. They're starting to talk less. They're starting to add less ideas. And some of these girls were just the most creative creatures we had ever seen. And so we had to try to counteract that. We put up what we called a failure wall in the room. And so failures were celebrated more than successes were celebrated for at least a year and a half. And it was kind of like, bells and whistles and candy or whatever like that. You failed something because we were trying to make them continue to stretch themselves and to, participate. It wasn't that they didn't want to participate. They would just keep getting torn away from it. And then they would start to second guess because the boys had spent so much more time in it. And that's a society thing that we have to think about. I mean, obviously, we need to socialize the kids, but that was the point. I had never been for single sex education ever in my life, and that was the point at which I went, maybe there's something to that, because then they're all going through the same social thing together. And that's when I started supporting the idea of, at least for young ladies, single sex teams in that particular area.
Really like your failure room. What a great idea.
Mm.
I don't know if did you overlap with Jay Whitaker? He was my graduate student, but I think you had left already.
I probably had
Anyway,
left already, yeah.
Jay ended up starting a battery company. He's a professor in Carnegie Mellon. And he raised like $200 million of venture capital money. I went to visit him, and he showed me his skunk works, or his research lab, and then his production facility. But we walked by this big, huge area with just all this junk in there. I'm like, "What is that, Jay?" He goes, "Oh, that's my failure room. That's really important to me. These are all so meaningful because this is how I learned everything." And he said, "Here's a 1930s hand grenade maker that I bought to figure out how to compact the powders."
Yeah.
And he just couldn't bring himself to throw any of it away because that's where he learned.
No, it absolutely is. And failure was the most important part. We developed a culture on our robotics teams that you fail faster to get, further, right? And it was all about, trying things out, multiple ideas at the same time. You usually had more than one robot. We had a robot that would allow us that wasn't part of the main concept, area. One that, for programming, trying things out. We had one season where we actually rebuilt the robot, tested it, programmed it every 4 weeks.
Wow.
That is an incredibly intense schedule. That's what the kids wanted to do. They were like, we're going to have to scrap this and start again. We're like, don't take it apart, put it aside. We'll get you some more parts, put the next one together so that just in case, so you can go to competition with that one, right? And then so they just became so fluid with that, failing, throwing away, no commitment to it. We became very famous for being what we called a team of parts, a kit of parts team. That's how they called it, kit of parts. Instead of CADing and building, like, a lot of people want to do some carbon fiber, things like that. Great learning and all that. But once you start CADing special parts and making them out of expensive materials, you're wed to that design. So we had art, and people would go, God, because we were one of the most winning teams in FTC history. And people would be like, how are they doing this with this, just the parts in the box? And I'm like, because we're not wedded to design. We fail, and tomorrow. And sometimes the kids would have a spectacular failure at an event, and they wouldn't leave the event until they'd taken the pizza boxes and drawn their ideas out of it, and they came up with a plan together, and they were going to implement it tomorrow. It's a culture. It's a state of mind.
That's
I love that. There's so I'm thinking of some people that I've known, like collaborators I've had, who just get so stuck on the idea. They're like, I have to make this work. No, sometimes you have to let
Yeah.
it go. Some
Sometimes you
ideas
just
are
have to let
just
it
not
go.
good ideas, but you don't know until you try. That's
Yeah.
okay.
Well,
well,
running a team, like an engineering team, is really about social dynamics and team dynamics,
Oh
as
yeah.
much as it is about the actual engineering. And I had a point at which I was trying to get the kids to think about what were they good at, not just good at, but they were kind of, how do I say this? I sat them all down and I had them do what I would call like a personality analysis. I made up this little chart, which I had this axis. One axis was loud talkers, and the other one was quiet thinkers. Because when you're on a team, there's people who are just, they spit stuff out without thinking about it. And there's people who, the sometimes it's the young lady in the corner who's thinking, and you can see the wheels are turning, and she's got the best idea, but she won't let it come out of her mouth until it's perfect. And so I made the kids put themselves on this axis, and then I had them give me all these phrases about what's good about being a loud talker, what's bad about it, pros and cons, what's good or bad about being the quiet thinker. And in the end, they identified themselves. They also realized that each of them had huge strengths on the team, each type of person did. And it just meant that we needed to apply those people in different ways. An example would be the loud talkers are awesome in the prototype phase because they are just spitting out the craziest ass ideas you can imagine. Prototyping, they're awful. They lead to something. Usually they lead to something. The quiet thinker usually figures out what's going to lead to.
Right.
But you don't have those people wire the robot because it's going to fail. There's going to be a wiring issue. So the kids would kind of like, the loud talkers would get much more heavily involved in the prototyping, and sometimes the quiet thinkers, we'd make all the loud talkers go away, and the quiet thinkers would have a good night with the robot and rewire the entire thing and label it, and it all be ready for competition. So there was a lot of this kind of thinking about these dynamics of the types of engineers and the types of engineers you need to make something, successful.
So we have all these, I'll just call them technical education programs for students that are outside of the classroom, but are very much helping them get ready with knowledge and skills for making things and for having careers. And I imagine some people might have the idea that that's a recent innovation, but technical
No.
innovation is, or technical education is very, very old. It's as old as technology, right?
Yes.
And there are these ongoing cycles in education of, oh, we'll do it this way. No, we'll throw out the model. We'll do a new way. And what are maybe some older educational things in the textile space, for example, where how did people used to teach technology, and are there things that we can learn about that in modern education that are practices we've
Well,
lost touch with?
yes. So um, this will take a couple minutes here, but in the 17th century, we had this explosion of merchants and entrepreneurs in England because the Protestantism came in. And what happened when um, there was all this fracturing of the Protestant religion in England, we had the major religion, Anglicanism, that people had to swear an oath to because it was the king's religion. So there were people who were merchants, et cetera, that, well, actually, I should back up. They weren't they were Quakers, uh, Presbyterians. They didn't adhere to the dominant religion. And because of that, they were boxed out of university education. And so what they had to do is become merchants and entrepreneurs. And so they were problem solving all the time. They were tradespeople. They were the metallurgists. They were the makers of threads. They were the all of the handcrafts. Now, they couldn't send their kids to certain kinds of education, and humanism was the type of education that was education at that period of time. So they started looking at other ways, and they started looking at practical education, meaning apprenticeships. So they started sending their boys at 12 years old into apprenticeships with other local tradespeople in order to educate them. Well, at the same time, so that the boys would go through and they would do their apprenticeship. They'd learn the trade, and then they would go out and get established themselves. At the same time, these religious, and this is a paper that I just wrote earlier this year, the girls were being educated as well. And there is this large amount of material culture, and for those who can see the YouTube, I've put on the screen these embroidered samplers, one of which looks like lace that's put together, and then a box which is entirely covered in really free form embroidery that's raised and has all of these figures on it. And this is a discontinuity in embroidery history, these particular objects. They're very complicated. People love to do them, but the box would take 3 years to do. And I've been really scratching my head as to why were these things done, because beforehand and afterwards, everything was very simple. Recently, I figured out that they were all being done by these merchant family daughters. And as I went down deeper into them, all of a sudden it hit me what was going on, and I went and found all the primary source resources to figure this out, that there was this big argument between the practicum, or we would call it the STEM education, versus the humanism, which is this rote way of education. It's rhetoric, it's the classics, it's translating between Latin and then back to your language, back and forth, things that were good for becoming a lawyer or a politician or a minister in England. And there was a huge debate in the literature at the time, if you really start looking for it, if you're familiar with the humanities versus STEM arguments today. So I started looking at the objects, which I do teach as well, much more from the principles of how do you teach programming and problem solving, or logic and problem solving. And amazingly enough, it completely flowed from that, each one of the techniques. And in the order that they were worked on it, to give you logic and problem solving exercises. So the first thing that the girls had to learn to embroider was basically an analog to a dot by dot game. And so they were learning sequencing, memory, and direction following. And then the next type of embroidery that they had to do on these things required them to do all this analysis and decision making, because there weren't any instructions that were printed at the time. So they were very complicated stitches, and when you change direction, today there's a book that allows you to do this by just flipping the page looking for the direction. But the order of the stitches, in order to turn a corner, there are 32 different ways to do it. And so the girls, because they wanted it to be reversible from the front and the back, the girls had to figure that out themselves every time they changed the direction of the stitches. That is incredibly complex. And then it continued going on, and we went through all of this in the robotics, teaching the kids, logical reasoning, planning, conditional thinking. It's because I tried to put together a course to teach this kind of embroidery that looks like lace, and it took me 1,000 pages to teach people how to figure out a pattern. And I was like, these girls, and the common thing that's being said about these girls at this time is that they're learning to mend. And I'm like, no, they aren't. They are learning very in-depth problem-solving methodologies. And why would they be doing that? Because they married men who were now merchants, tradespeople, had a whole bunch of apprentices. They were manufacturing things. And the men, by the time they had the capital enough to marry a woman, they married a woman who was about 15 to 20 years at least younger than them, and they tended to die, and the woman had to take over the business. And when you start going through everything, and this is in the 1600s, The women are taking over the businesses. They're taking out insurance policies. They're doing everything. They're running the financial life, and they run the financial life for the family going forward. So they had to be equipped with everything that they needed, and so they were sending the girls through this, and this was a big piece of how education started to develop into this two different areas where you have this STEM practicum and this humanities humanist way. And I'm studying right now a group of pattern book makers for embroidery in Nuremberg, Germany. And the reason I'm doing that and their embroideries is because they're also known as scientists. So one of them is Maria Sibylla Miriam, who is the world's first entomologist. And she was an embroidery teacher. So it really makes you go, huh. And this wonderful woman who was this fabulous astronomer as well. So it goes hand in hand. These technical skills, the hand skills, the problem solving learning, and then of course the sciences and engineering.
So, do you think you could talk a little bit about your company? Because that's what you're doing now, right? Thistle Threads.
Mm-hmm.
And I went to the website and I see it's almost like a whole university, right? You even call it an online university.
Yeah.
So
yeah.
besides selling products and things like that, you're really involved with writing and teaching and researching. So
Yeah. Well, Steve, I sat down with Ron Gabala once and Dave many years ago, and I said, hey, it's interesting that Heather Leckman did this materials archaeology and anthropology subfield at MIT. What do you think? How would I pitch myself as a professor somewhere? They could not figure out how I could shoehorn myself into a university setting. And I was not willing to give up my interest in historical research and materials research in the historical context. So I decided that what I would do is I would form a company that would pay myself to do that. So the picture is I go into the museums and I research objects. Sometimes I'm researching in textile conservation departments and I'm involved on visiting boards and several of them, or as an expert, and we'll be researching these pieces of embroidery. I then look at it from the standpoint of what were the materials, do we have them today? What were the techniques? They're very difficult, and figure it out. And then I might go to Europe to the old companies, some of which do take their roots all the way back to the 17 and 1600s. And I work with their equipment, usually, which is, by the way, 1800s equipment. And we remake the threads of that time frame iteratively. And sometimes I will find some parts of equipment that I could remake, or kind of make some of my robot guys help me make some of my equipment and prototype. This is the engineering part, right? Prototype engineering, and then send the prototypes back to Europe to be made. So I make all the threads again, bring them back, cut them up, design with them, teach from all that information from the historic embroidery, the techniques that I'm trying to decode, write the courses. That's where the online engineering comes. But while I'm doing that, my head is really thinking about the history piece of it, right? And so I'm researching the history piece. And so I always do my courses, which is my main moneymaker, where I have the technical projects or technique learning with history sections, which are my initial rough draft of whatever I'm trying to get to, which is, of course, either academic papers or hopefully books to come. Please, if any publishers are out there, love to talk to you. Otherwise, I'm going to have to, I may be starting my own publishing house in order to do this. And so the students buy the projects, they also buy the threads, they go off to do their own things. And I've launched through a few major projects where I looked at objects and said, hey, this has got the possibility of really telling us some history if we can remake it again. After I did the Plymouth jacket, the whole textile community, especially the embroidery community, knew I could pull stuff off. That was the takeaway from that, because all the threads were manufactured for that. I figured out all the mechanisms to get that done pretty easily. So I picked these boxes. It's called an embroidered cabinet. It was what the girls did when I was just talking about this humanism versus STEM education in the boarding schools for the nonconformists in England. They ended their schooling with this embroidered box that was creative. They just got the outline of the design on it, and then they had to figure out how to do it themselves. And they needed tons of threads to it. And I was like, God, why? Who was making the boxes? Why? There was so many historical questions that I was looking at with it. But also, I knew that it was a very marketable object, meaning that every woman who's seen one, or other stitcher, I have many male stitchers as well, wanted one. And when they're in good condition, they go for about $250,000 on the antique market. And if they're in bad condition, like almost rotted away, they're $10,000. So people would pay for a decent class. And I have about 1,400 students making them worldwide. And I had a wonderful cabinet maker who made me the cabinets for them. But I had to go through everything. So every piece of it has been a research project. How were the locks made? Work with a historic locksmith, remake the locks, CAD them, X-ray them, etc. The bottles that go in, the tapes. Every single thing has been a research project, but now I'm down to the point where I know what was going on in London at the time to build this whole infrastructure. Because what's written about them is, oh, the girls were making a box, like making a kit, like they were going to cut the wood themselves. I'm like, no. There's something much more in depth at this particular point. But that's why it's called online university, because usually people are just they've made a project, it's cute, and people take it and they make a replica of it. And this is much more than that. This is really in depth, but it's all from the fact that nobody will give me a professorship.
Well, maybe you should try Thomas Jefferson University.
There we go.
Because they have pretty wide-ranging programs. I'm sure you've seen.
Yeah, they do. Yeah. Well, it's that humanities are they're a little siloed at the moment. And I've actually had a lot of trouble publishing my work because they'll look at the paper and they'll go, oh yeah, half of this fits into what our journal does, but you've got equations in here. We don't do equations. We're humanities. I even got one paper back, which is going to be published in the next week, which had scrawled across it, there is no room for the sciences and the humanities.
Oh my God.
And I know that
Where do you think the sciences came from?
Yeah. It's tough because they've developed their own little like points of view on things. And not to say that engineering fields haven't done the same thing.
Right.
But coming in with as a multi-dimensional, thought process, using economic history, using material science, using math, using, primary source research, using biography, and all putting that all together, there's no real good place for it. And it doesn't fit in somebody's, it's a square peg in a round hole. And so that's been a challenge for me.
Yeah, that's still a very big problem in modern engineering education that we deal with, is we want our students to think about societal consequences of engineering work. We want them to think about user experiences and sociological factors, and
absolutely
the fact that material culture is what decides what people will and will not use. It doesn't matter how well it works, it matters if people want it. And to get students to adopt that way of thinking and realize that there's more to life than technical solutions is a huge challenge.
And it goes the other way, right? The other way. Like I know why Dave chose you as a graduate student, because you had been studying polymers your whole life before you got to Dave. They were just called thread, right?
Yes.
And you were already thinking about how they wrap in 3 dimensions and how they lay out. And that is the fundamental underpinning of how, I remember Dave getting all excited about the windings of the wire for the Brooklyn Bridge, right? Because it was a lot like hair and how things wrap around. And he went into this deep dive of winding technologies. But of course, where did that all come from? That all came from textiles, right?
Exactly. Yeah, I get excited about the weirdest things myself. Yeah.
Right, but it's really important, and it shows up in biology and all these other things, and it even it even starts to make you think about mystical connections.
Mm-hmm.
Why are, proteins, why the structure of hair is, intrinsically connected to how we do the windings of a, you know, bridge cable.
Right. Well, I'm fascinated by silk, and of course, everything. The majority of polymer science comes out of and is trying to replicate either silk or wool in the early days, because you can't have enough. There's just not enough acreage for sheep. I reviewed a book on sheep recently. We can't. We have to have non-natural fibers because we just have too much population, not enough sheep that can make good wool, and then silk. And it goes down to that structure. And I'm trying right now to um, teach the structure of silk to all the embroiderers, because they can't embroider right until they understand silk at a much more fundamental level,
Huh.
or even thread construction. And so I've had to design a whole series of projects in order to walk them very slowly through these concepts of the structure of silk and how silk threads are used and made and used, putting
Did
over
you
twists
see
into
the
things.
exhibits at the what's that thing at MIT? Their media lab. What's that called?
The
So
Media Lab, yeah, yeah.
yeah,
I,
maybe that's so Neri Oxman's thing
yes,
on
yes, I've,
silk.
I've lectured with Neri before. Yes,
Yeah,
yes,
that
I've
was
seen. Yeah,
amazing what she
amazing,
did. And
amazing.
she got into how the silkworms make silk and their
Yeah, and
behavior,
just
and then
yes.
she let them go.
Well, I'm right now working on a piece with the Smithsonian. I purchased a embroidered piece, a sampler that a girl did in Charlestown, Massachusetts, and at the bottom of it she stitched "Made with American silk." It's not the best looking piece in the world. Well, it's not the best looking piece in the world because it was made with American silk, meaning people who cultivated with, mulberry leaves and silkworms on the East Coast. And it's actually not that easy to process silk after it comes from the cocoon.
Hmm.
And so we've been looking at trying to figure out exactly which group of people, mill, et cetera. Looking at the back of the embroidery, we can see the serakin on it and all of that. And it's only one of 3 objects known to have been made with American silk. So
Wow.
they're working with me on it because they want it. We're not done
And
with
of
it.
course, when
But
silk started in China, it was a trade secret that
yes.
if you gave up the secret, you would be killed.
Mm-hmm. Mm-hmm.
And so
Well,
the archaeologists have discovered all this culture about, silk technology.
yeah.
It was,
It's
highly
really
guarded.
interesting. It
Yeah.
is. It is. Well, it's interesting because we were a dramatic failure. The first wave of people that came over to Jamestown, one of the purposes was actually to cultivate silk as one of the potential cash crops that they
Huh.
could do. And so there's all these wonderful details on the engineering of silk that was drawn up at that period of time. But over and over again, there were these efforts in the United States to try to cultivate silk. And we did so poorly at it because it's just a really labor intensive thing to collect the leaves. You have to have the right mulberry leaves. They grew the wrong ones sometimes. Um, that they ended up starting to make instruments, apparatuses, machinery to try uh, to reel up the materials. And so we ended up sending all of our equipment. We ended up having an industry that built the equipment for silk reeling, et cetera, and selling it to China because we couldn't cultivate, but we tried to mechanize it, and we
Right.
mechanized it very well. So all those patent machines are over at the Smithsonian at the moment. But
Yeah.
it's interesting how history and colonization and all of that impacts materials.
Right.
Yeah, I wish we could talk about silk for another hour, but
Yeah,
unfortunately, the clock is yelling at me.
Yeah.
yeah.
Um, Before we do call it a day, though, just because you have so many fingers and so many pies, all of these different interesting projects and companies and ideas and topics, is there something that we didn't cover today that you want to put out there and say, hey, internet, I have this cool thing also that I want to tell
Mm.
us about?
Well, I think that one thing, Tim, I think you and I have talked about it a little bit over at University of Michigan, is I wish people would think about um, this concept of big projects for kids and pushing it. We kind of do it like, oh, well, you're going to get your PhD, you're going to synthesize all this information, and that's now you're going to be a PhD. We can do that at younger levels and produce better educated kids, better problem solvers, more creative kids by pushing that idea down, whether it be um, taking the capstone project concept that a lot of engineering colleges do in senior level, pushing it as far down as possible, working on things together, pushing it into the high school, pushing it down even into the elementary school. I um, I think that is, and it doesn't have to be engineering. It doesn't have to be robots. It just has to be a large, unbounded problem that a kid works on for a period of time. It could be history that they're interested in, it could be music that they're interested in, it could be embroidery. But working on something for a long period of time and having to come up with the problems and get over them gets you to a better, well-rounded, educated, person. And I just wanted to state that. I know you guys are,
Couldn't
are
agree
true
more.
believers. Couldn't agree
Oh,
more. I know.
absolutely.
Yep.
The value of slow thinking is so important and gets so ignored today because everything can be fast, 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 more and more, make the numbers go up. Yeah, but there's something that comes from
Yeah.
spending a few hundred hours with a problem that you can't get that experience any other way.
Oh yeah. Have you read Every Tool's a Hammer, which is I think by he's the Mythbusters guy. I can't remember which
Oh,
one.
okay. Is it Adam?
It's Adam
Adam
Savage.
Savage. Yeah.
Best book I ever read about creativity, which it does not sound like creativity, but it's exactly how creativity happens. His book. Um, but
Well,
yeah,
this all sounds a lot like research. And like Ron Cantor taught us, there's a reason it's called research because you
yes.
search and you search and you
And you
search
search.
and you
Well,
search.
well, what you're not saying here is that the research is that you fail and you get back
Yes,
up and you try again and you learn
right,
something from it and you try again and you're
right.
beaten down and you try again.
But it's that
Failure,
repeat
huge.
that's
It's that
so
repeat.
important.
It's so
Just like
important.
crystals. Just like
Yeah,
crystals.
yeah. Repeat, repeat, repeat.
All right. I think that's enough of that.
All right. Well, thank you very, very much for being on our show. And
You're
thank all
welcome.
the listeners out there for hanging out with us. And thank you.
All right. Thanks a
Yeah.
lot.
So, all
Been a
right.
pleasure to have you here. To everyone else out in the audience, of course, we'll see you on the next episode of Undercode.